What's up everyone? Welcome back to Math World. So we're going to continue from where we left off in the last video. So at the end of the last video, we actually finally found the domain of the function y equals, or we can call it f of x, which is equal to sine of x all raised to the sine of x power. And we claim that the domain will be the following set, which are actually infinitely many open intervals that satisfy the conditions x plus 2 pi n, such that x is lying between 0 and pi, where n is just any integers. So this is equivalent to say that we have open intervals from 0 to pi, and then with or union with the shift of such interval by multiple copies of 2 pi. So we can union with adding 2 pi's on both sides so that we get from 2 pi to 3 pi. Or we can actually subtract 2 pi and get the open interval negative 2 pi to negative pi, and so on and so forth. Also, we found out the 4 different values inside of the period of sine, such that those 4 values will actually have the first derivative of the original function being equal to 0, which are arcsine or sine inverse of 1 over e, and then we also have pi over 2 or 90 degrees. Also, we have pi minus arcsine of 1 over e, and as well as 3 pi over 2. Now, we also said that we don't know whether all 4 values inside of the pink box will be lying inside of the domain. And that's also a reason why we need to check our domain and then to figure out if there's any extraneous solutions inside of the pink box. Since inside of our domain, we have the open interval from 0 to pi, and after that is just a shift of the period of sine. So as we only consider of the period of sine function here, which is from 0 to 2 pi, and in this case we can make it a semi-open interval. Choose one side to be open and one side to be closed so that we actually don't get repeated as we shift the interval. Anyway, if we consider inside of one period of the sine function, we have these 4 values, but only from 0 to pi, the open interval, meaning that if we exclude the 2 endpoints, all the values inside or in between 0 to pi will be part of the domain. So if we go back up here, by definition, the sine inverse function has the output or the range from negative pi over 2 to positive pi over 2, and if the value inside of the inverse sine function is positive, then the outputs that we get for the inverse function will also be positive, meaning that in this case we will actually have the value between 0 to pi over 2, and it is a positive value. And we see that that will be inside of our domain, as our domain is actually from 0 to pi, which is actually covering the value that we have. Now for the second value, we have pi over 2, and of course pi over 2 is between 0 to pi, so that one is also good. Third one, we have pi minus sine inverse of 1 over e. As we claim that sine inverse of 1 over e is some positive values between 0 to pi over 2. This value here, when we have pi minus some positive value, we know that this value must be strictly less than pi. So it is not equal to it is not going to be equal to pi. So it means that at this point, if it is satisfying, it will be lying inside of the domain, but not to the right of this domain here. Now we also need to check if it's going too far left, that is actually running outside as well. But since we're saying that sine inverse of 1 over e is a positive value that can not be greater than pi over 2 by the definition of sine inverse function, this value has to be this value here, the arc sine of 1 over e, has to be less than pi over 2, or less than or equal to pi over 2. And we're saying that it's positive, so we will actually get this. So if we actually take the negative version of it or multiply both sides by -1, we actually get negative of sine inverse will be, now as we multiply everything by negative, we also need to flip the sign, right? So we have less than 0, but greater than or equal to negative of the right hand side. So if we actually switch the order, we get negative pi over 2 is less than or equal to negative sine inverse of 1 over e, which is strictly less than 0. So if we consider this value, pi minus the sine inverse, we're going to add pi on both sides, which gives us the right end is what we just claimed, has to be strictly less than pi, because now we add pi on both sides. Where the left end, which is what we're trying to check, will give us pi minus pi over 2, which is what we have here. So we get pi over 2. That means this value here is actually a line between pi over 2 or 90 degrees to pi, but not equal to pi itself. So that we can see this value must be inside of this domain 0 to pi as well. Good. Meaning that we need to keep this value. It is still part of our it's still lying in our domain, and we need to consider the other stuffs that is related to this value here. However, now if we try to check our last parts or last solution, 3 pi over 2, we of course see that 3 pi over 2 is greater than pi, but it is less than 2 pi, which is the left end or the lower bound of the next interval. So what does that mean? It means that 3 pi over 2 is right in between, but it is not inside of our domain because it is not belonging to any of the intervals that is part of the domain that we have here. Therefore, for all 4 answers that we have, sine inverse of 1 over e, pi over 2, pi minus sine inverse of 1 over e, and 3 pi over 2, there's one solution that is actually not satisfying our condition, which is 3 pi over 2. So now we actually can take off 3 pi over 2 because it is not part of the domain. We don't have to consider of it anymore. It's not going to be shown in our graph either. Good. That means now we only have 3 points left to consider of where those 3 points have the first derivative of the original function equal to 0. Meaning that now those 3 points will be our relative extrema. So here we go. Next question. Relative maximum and relative minimum. We're going to do both of them at the same time. And again, how are we going to do it? 2 ways of doing it. One way is, of course, take the second derivative of the function so that we are now going to see what sign we get for a second derivative for each of the points we chose. And the sign of the second derivative will determine whether it's concave up or concave down at such point, so that we know whether it will be a relative maximum or relative minimum at each point. But as you can see, we actually took quite a long time. We actually spent quite a long time to do the first derivative already. If we try to take the derivative of the first derivative function, we'll actually spend even longer time. So we're going to do it with the second method, which is making a table. So again, we're now only considering inside of one period, because we can just shift the graph by one period, so that we and continuously, so that not continuously, repetitively, so that we will be able to generate the whole graph eventually. So now, if we consider the actual function, and also we have to, of course, consider the first derivative, we get the first derivative at those 3 points will be 0. So we're going to get something like this. We have the first point, which is sine inverse of 1 over e. And then we have the second point. If we're going in an increasing order, it will be pi over 2. Great. Last but not least, we have pi minus sine inverse of 1 over e. And again, we already knew that the first derivative at those 3 points will be 0. So in order to determine whether they're relative maximum or minimum, we need to choose some points in between the 2 points that we have, meaning that we're going to choose some points in the 3 dots. Any points will be fine, and then we're going to check what sign we get in the first derivative at such point, so that we will be able to tell whether the graph is going up or going down in that open interval. So right now, we don't know whether they're relative minimum or relative maximum yet. So we're going to choose some points. First, let's talk about some values here. We know that e as a natural number is numerically approximately 2.178, which is of course less than 3 but greater than 2, right? Meaning that e is strictly greater than 2. So, ladies and gentlemen, we can actually consider of the following. If e is greater than 2, we have 1 over e will be less than 1 over 2. Or if we take the reciprocal of this, reciprocal of 2 or 1 over 2 will be, now we need to flip the sign here, greater than the reciprocal of e, which is 1 over e, so that we get the relation 1 over e is less than 1 over 2. Of course, you can actually just divide both sides by 2e to get the same results here. Okay, but what does that mean? Actually, before we move on and talk about what it does, we need to talk about some properties of sine function as well, because we know that sine function is a monotonic increasing function, meaning that it's always increasing as we consider within 0 to the peak, which is pi over 2. Okay, when x is equal to pi over 2, it hits its maximum, and of course when if we consider the open interval from 0 to pi over 2, the whole graph is increasing. In fact, it actually looks this way, like this. So as sine being an increasing function or monotonic increasing function, when you consider the inverse function of it, is also a monotonic increasing function, because again, if we consider a graph, the inverse function will just flip it this way, like this. Okay, so since it is a monotonic increasing function, it means that as x getting bigger and bigger, the y value will also get bigger and bigger, or output will also get bigger and bigger. That means when we have 1 over e is less than 1 over 2, we can just plug in the inverse sine function here, which actually gives us the sine inverse of 1 over e is also less than sine inverse of 1 over 2. So this is telling us that sine inverse of 1 over 2 has to be between here and here, because it has to be strictly greater than sine inverse of 1 over e. But then we also know that this is not going to be pi over 2, because pi over 2 is equal to sine inverse of positive 1, which is even greater than this. Like so. So we now have this value, which is lying in here. So we can actually, in fact, use this value here to help us getting what sign we will get for the first derivative of the function. So this is what we're going to get. We know that sine inverse of 1/2 is 1/2 is a special value in the trig function table. And what angles do we get? Well, what angles between 0 and pi over 2 will satisfy that sine of the angle is 1/2? 30 degrees, or pi over 6. So in fact, this is equal to pi over 6, and we are saying that pi over 6 is actually lying in this open interval here. So we can use pi over 6 as one of the values to help us to check the sign itself. Okay, again, this is helping us to check the sign, not the actual value. So we do not have to choose any specific values as because they all generate the same sign. So if we substitute in to our first derivative function, we have f prime of pi over 6 is equal to the following. We have sine of pi over 6, which is of course 1/2, raise it to the 1/2 power, times cosine of pi over 6 is actually same as sine of pi over 3. And to do that, we can actually consider the right triangle, and it's also one of the special angles. So we actually will end up with the special values. Okay, then we have times the third term, 1 plus ln of sine of pi over 6, which is same as ln of 1/2. Good. So again, since we're only trying to check the sign of the first derivative, not the actual value, so we don't have to calculate the whole thing. We just need to consider what sign we'll get. So the first part, 1/2 to 1/2 power, this is clearly greater than 0 because of the property of x to x power function. And then the second term is also greater than 0. Again, that is because we have a positive value here, right? The question is, what sign do we get for our last factor? So how do we do it? Well, we have 1 plus ln of 1/2, but 1/2 is same as 2 to the negative first power, so we can rewrite as 2 to the negative first power. And by property of logarithm, we can just throw in the exponents to the front to give us -1 times ln of 2, which is negative. So we'll actually change the sign into 1 minus ln of 2. Now again, why is it important? Because we know that 2 is less than e here, where ln of e is equal to 1. So ln of 2 will be something that is strictly less than 1. Okay, so how do we do it? Again, the logarithmic function or natural log function will also be a monotonic increasing. So we don't have to flip the sign as we put ln in front of the values. So we actually end up with ln of 2 is strictly less than ln of e, which is by definition equal to 1. So we see that this term is less than 1. So we have 1 minus some values that is less than 1, so that we still have something left over as we subtract, meaning that this whole term is in fact greater than 0. So it means that this product will be the product of all positive integers, positive values. So we have positive times positive times positive, giving us the whole thing is also positive. Then we can now fill it up. Here we get a positive value, meaning that the original function y is actually increasing as we continue moving up. Okay, don't know whether it's concave up, concave down, but it doesn't matter, it's increasing here. So we can actually use the same method to figure out the rest of the signs in each interval, each open interval, so that once we complete it, we'll be able to determine whether we get relative maximum or relative minimum for each special values. And I'll pause the video right here. So from the beginning of next video, you'll actually see a complete graph. So in the next video, at the beginning of next video, you will be able to see a complete table here that actually shows what signs we will get on the first derivative in each open interval, as well as the direction of the graph of the function pointing in each open interval, so that we will be able to determine the relative maximum and relative minimum inside of each interval. So as I said, this video is very long and I have to open another part or another video to continue talking about this. Yeah, that's it for this video right now. I will see you guys in the next video, and please don't forget to subscribe to my channel to find out more of my other videos. And if you have any thoughts or comments or something that you want to talk about, especially something that we have done in this video, you can leave your comment below. I will see you guys in the next video.